This is the 5-4 to 5-5 review, the last free response, number 10, and calculators are allowed. So we're given the volume of a spherical hot air balloon and how it's expanding. So we're given information about the rate at which that radius is changing, it looks like. And we're on a closed interval from 0 to 12. And in part A, we want to estimate the radius of the balloon when t equals 5.4. So if we read the information, we are given an initial radius. So we're given that r of 5 is 30, and then we're given information about the rate at which that radius is changing. So we can write the radius at any time. Oops, that's 30. Excuse me, as 30 plus the accumulation from 0 to t on that r prime function. So in part A, it says we want to estimate it using the tangent line approximation at t equals 5. So because we want a tangent line, that means we're going to do a point and a slope on the graph of r. So when t is 5, we know that r is 5, 30. And the slope will be r prime of 5, which we can go look up here, is 2.0. Once we've got the point and we've got the slope, we can write the equation of the line, which is the slope times x minus 5 plus 30. And we can now approximate the radius at 5.4 as the y that comes out when I plug in a 5.4, which will be 2 times a 0.4 plus a 30. I get a 30.8 centimeters, or feet, excuse me. It's a big balloon. Okay, next part, B. Oh wait, is your estimate greater than or less than the true value? So the thing that tells us whether or not a tangent line approximation is too big or too small is the concavity of the original function. So if we go back up here, it says that the graph of r is concave down. So since r is concave down, that means my picture is frowning and I have a tangent line above it. This estimate from the tangent line, oh sorry, let me skip this. This estimate from the tangent line is too large. So it's greater than the true value. Part B says find the rate of change of the volume with respect to time when t equals 5. So we know that volume is 4/3 pi r cubed because it's a spherical balloon, and rate of change, when we want to find it with respect to time, that's telling us to take the derivative with respect to t. So we'll have dv dt equals, we want to take the derivative of this, so we'll move through the constant. Then we hit the power of 3 inside unchanged. Then we have to multiply by the derivative of the inside. So if we want that evaluated at 5, then dv dt evaluated when time is 5 is going to equal 4/3 pi times 3 times r of 5, which we knew was 30 from up above, squared, times r prime of 5, which we also figured out up above from the table was 2. If I multiply this all out on my calculator, I get 7,200 pi, and the unit, since we're doing volume, will be feet cubed per time, and time in this problem is measured in minutes. Next part, C. C says use a right Riemann sum with 5 subintervals indicated to approximate the accumulation of r prime. Then we want to talk about what that means. So I'm going to start by just doing a sketch of r prime. So we'll come back up here so we can see it. And my sketch is going to be a little rough, but it'll give you the general idea. We have a 2, a 5, a 7, 8, 9, 10, 11, and a 12. and it looks like at 0 I've got a 5.7, which will be about here. At 2 I've got a 4. 1, 2, 3, 4. At 5 I'm at 2. At 7 I'm at a 1.2. At 11 I'm at a 0.6. And at 12 I'm at a 0.5. So we can kind of see that that graph of R prime, which is measured in feet per minute, where the input is in minutes, we can see that that's a decreasing function, and it asked us to estimate the accumulation from 0 to 12 using a left-hand Riemann sum. So left hand, I think it was left, let me double check here. Oh, sorry, it was a right Riemann sum. So that means we're going to cut using the data that we have, and then we're going to do a right Riemann sum. Now notice that not all the rectangles have the same width, so we're going to have to do them separately. We'll end up with that accumulation is approximately the area of the first rectangle, which is 2, the width is 2, the height comes from the 4, plus the next width is 3, and its height is 2. The next width is 2, and its height is a 1.2. Then the next width is from 7 to 11, which is a 4, and its height is a 0.6. And then my last right edge, the width is a 1, and the height is a 0.5. So if you don't want to draw the picture and you just want to go from the graph here, we want a right edge, which means we're going to be using the right endpoints, and then we'll be multiplying by the width, which is the distance between these two. So we have a 2 and a 3 and a 2 and a 4 and a 1, and each of those gets multiplied by the respective right edge. So if I multiply this all out, I end up with 19.3. Now we need to talk about the units. Well, notice that we're doing a height that's feet per minute and a width that is minutes. So if I multiply those together, the minutes disappear and I'm left with just plain feet. And we want to talk about what that accumulation represents. Well, if we accumulate R prime, that's like the antiderivative of R prime, that's going to be R. So we can say that this is representing the net change in the radius, and the net change was positive. So this 0 to 12 R prime of t represents the increase in the radius on the time interval from 0 to 12 minutes. Okay, last part, D, says, is your approximation in part C greater than or less than? So if we look at our approximation and our picture, we can see that the reds are all underneath. So for part D, we could say our approximation is smaller than the actual value. Now, why do we know that? We know that because we computed a right Riemann sum approximation on a decreasing function. If the function is decreasing, then the approximation will be less.